All right, guys, so today we're going to be talking a little bit about torque. First of all, just make sure that you're spelling it right. All right, there's no W. All right, torque. That's the idea. So a torque is essentially a cause of an acceleration in rotation. All right, so we're going to change something's rotational motion. All right, so rotation is a little bit different than the linear motion we've been talking about. So let's take a look at how. So one of the first things we're going to need to talk about is the center about which something spins. All right, that's called the axis of rotation. All right, so let's just kind of define that right over here, axis of rotation. In this case, that's the center of this hex nut. Maybe it's the center of a bicycle or a football or whatever it is that's rotating. Okay, so that's going to be the center. We call that the axis of rotation. Okay, where we apply a force is also going to come into play. So if we apply a force, let's say that's straight up in this case, that's going to be kind of our best model. All right, so if there's our force, force arrow, right, that's going to be F. So that's our force. So the force is going to try to cause this wrench to rotate around, okay? Obviously, the larger the force, the greater the torque, all right? So if we can increase that force, we can increase the torque. We'd be better at rotating this if we increase that force, okay? The next thing we need to look at is how far away is that force being applied to the axis of rotation. So the closer it is, the harder it's going to be to rotate. Okay, so it's, oops. This value right here is the distance between those two spots. Okay, so this value right here is d. It's the distance between the axis of rotation and the force. All right, d. For right now, we're just going to call that the distance. All right, we're going to have a better term for that in just a few minutes because when this is at a right angle, there's a special name for it, okay? So when this is at a right angle, there's a special name for it. That's where we're all right now, but for the moment, I'm going to leave that labeled D. Okay. And so we see that this angle also makes a difference, okay? So this angle is also important. Now, if we increase this distance, then we're going to have an increase in torque. All right? The farther away we are, the more leverage we have, the better we will be at causing a rotation. This angle, we can see that if we change this angle, it's really going to change. Okay, if I change this angle by twisting it, actually let's do the extreme, let's say this way, well then, hey, that's not going to be any rotation at all. That's just going to be forcing the wrench onto the hex nut. If I push it this way, if I apply the force in the opposite direction, well that extreme's no good either. That's not going to cause a rotation, that's just going to move the wrench, right? And everywhere in between is some portion of that. So I'm going to leave that shadow there, but I'm going to twist this over so that it's facing this way. And we're just going to move this over a little bit to there. Okay, so technically now, we're no longer at this right angle. Okay, so technically now this angle is different, right? So this is going to mean that part of that force is really not helping to rotate anymore. So if we extend this force line, and now we just evaluate the distance, the displacement actually, between the axis of rotation and the perpendicular application of force, right there. Well, now we've got a right angle. So this has a definition. This is a specific definition. This R value, all right, this R value is going to be d sine theta. It's kind of like just looking at the component of d that is perpendicular to the force, all right? And that's what we're going to be looking at. So this R value is called, and sometimes there's a little perpendicular symbol right here, this R value is called the lever arm. Okay, so we can look at this equation two different ways when we put this together, because as we increase that lever arm, we also get that increase in tau. We also like to see the angle at 90. All right, that's why we're kind of looking at the sine, because sine of 90 is 1. That means the entire force and the entire d value are working together in their best, like the optimum way, right? So right here, it's only the component of that distance. So our equation can be stated kind of two different ways, okay? So torque, which is, it's a Greek tau, it's kind of a squiggly t, all right? Tau equals force times r, all right, if we're looking at the perpendicular, or tau is FD sine theta, okay? With most of these problems, we're going to see that there's, they're going to be either at 90 assumed, or it will give you an angle, okay?